And Justin, you're muted.
All right. Thank you, Lily. Can you hear me now? Yeah, my instincts are to mute all the time on Zoom. Thank you all for showing up at this fun occasion for me. It's been a little stressful, I'll be honest. I have never taught this course before. I've given many lectures on topics in oceanography and on climate change. This is a topic very dear to my heart. I have worked on it quite a bit many years ago, and it's been quite fun to get back into it over the last few days to put together this presentation. What I want to point out is the website. I don't know if you can see it. I've got a little bit of the screen blocked, so I'm not seeing the whole thing. Are you seeing the Evolutionary Thermodynamics website?
Yeah, we can see the homepage with a beautiful plant.
Okay, it's got a plant there. So the key thing I want to show you here is the papers, and there's a list of papers here that would have been your homework had I been able to do this before the class. What I'm going to do is, for anyone who's interested, I'm offering in a month a free Zoom session with me. It can be outside of the college, where we'll go into these topics just to have a rousing discussion for anybody who digs into some of this literature and wants to come. So I'll host the Zoom session. It's mentioned here in events on this website. So there's the Bethel class. So this discussion on the 25th of April. And I'll put a Zoom link in here on that page, and also we'll post it. I guess that's the best place to post it. But if you contact me, my email is, you can contact me through this Evolutionary Thermodynamics website. Then library here, I have to get this moved so I can click on it. The library is the presentation that I'm going to give to you tonight. So you can scroll right through this thing. There's 66 slides, and you can just click on them. They go one at a time. So you can actually go to the site right now if you want and follow through with your own presentation. You can download it. You can check out and have the whole thing there to read tomorrow. So I'm going to go back and give the presentation from my PowerPoint slides directly, but I wanted you to know that you have access to all of this on this site that I just created. Oh, and these papers are quite interesting, by the way. Particularly, I recommend to you that the ones that are AIM3, AIM3, and IM3 are two papers I gave in Amsterdam in 2007, 2009, a little bit merging this topic with issues of human dimensions of global environmental change. And but the real meat would be in this paper by Nicholas and Prigogine. Prigogine really being the major scientist in non-equilibrium thermodynamics. So that's a meaty paper. This one by Bohm would be fascinating. All of these are good papers, and I'll be adding to this list as I bring other literature in. So I will now jump into the slideshow. Is this all coming through okay? Do you now see a full screen slideshow? Do I hear a yes from anybody? I hope so.
It's blank for me.
It's blank?
For me.
Okay, then I've got to do stop share, and I'm going to share screen again and get to the PowerPoint presentation. Is that working?
Great. Yep. Now we have it.
Yep.
Okay. So I'm going to go very quickly through these slides because you have the whole presentation available on that website. And I'd like to get to say 10, 15, 20 minutes of discussion at the end for people who have questions. Pipe up. I can't see hand waves here. I've got the screen open, but Lily can open your mic and ask me questions as we go. But if you can hold questions, that'll be better. I can whip through it. And now this isn't advancing. There we go. So most of you probably have heard of the field of thermodynamics. And I want to distinguish thermodynamics from evolutionary thermodynamics. I would say evolutionary thermodynamics is a subset or a sub-branch of thermodynamics. So basically, thermodynamics is the relationship of heat, temperature to energy and force and work. And it's the study of these systemic properties and the shifting aspects of energy in the system. So evolutionary thermodynamics is really the science that studies energetic systems in nature, and these would be non-equilibrium thermodynamics. We'll see that much of thermodynamics has been built up over the centuries thinking about equilibrium systems. So these are called closed thermodynamic systems where you don't have energy leaking in and out with the environment. And that's allowed scientists to study the relationships of work and heat. Gets a little thornier when you get out into an open natural system. And one of the things we see is that nature's doing something quite astounding, really, in the area of thermodynamics. So evolutionary thermodynamics really gets at what is life? Is energy itself alive? Are all energetic systems alive? We'll talk about what is an energetic system. Are human organizations following a fundamental principle related to evolutionary thermodynamics? Is global environmental change perhaps inevitable? Can humans even prevent global climate change? I'm going to try and remain optimistic through this, but there will be some serious questions posed in here. Just by way of quick background, I started into this research while I was ensconced in the carbon dioxide research group and the climate change group at Scripps Oceanography for a decade. And I tried to get my advisors to take this topic more seriously than they were willing to. They considered it more philosophy than science, and I believe it needs to be made into science. So very quickly, the 21st century research questions here will have to do with patterns of energy flow in the subsystems of human society. What about the patterns of growth and stability, particularly looking at energy through flow in a system, that's energy coming in to a subsystem, and we'll talk about subsystems as a part of systems. Particularly what leverage points in these subsystems can we access to help ourselves control what's going on technologically and in terms of energy use in society. Given the various instabilities and other difficulties, how are these effects potentially going to cascade? So I'm not going to cover all these research questions, but that's really why evolutionary thermodynamics is a ripe topic for this century. So very quickly, this, background on thermodynamics in the 1600s, force was being studied by Newton, and he came up with the famous equation, force equals mass times acceleration. So we give as a force unit, the Newton is an element of force, and that's 1 kilogram at meter squared per meter squared. So that's an acceleration. Meter per second is I'm sorry, I misspoke. It's meter per second is a speed per second. So that's an acceleration. Then they came up years later with the dyne, which is another unit of force, and related to dynamo and dynamic, for instance. And you can equate then the force of a Newton versus a force of a dyne. Letting Mr. Smith in. So in the 1800s, the work began to focus more on concepts around energy and what was energy. And Rudolf Clausius proposed ergon, which came from Heraclitus, a Greek word, as a unit of energy, work, and heat. Maxwell and Thomson, famous physicists, also pushed for centimeter, gram, and second as fundamental units of distance, mass, and time. So an erg was defined as a gram centimeter per second per second. So there you have a force through a distance. So the idea of energy being a force exerted through a distance became the dimensions of the concept. Then you also have a joule, and we'll mention joules later. It's another measure of energy that's much more popular right now when we talk about global energy. We talk about exajoules, and we'll equate that with the amount of energy in a billion tons of oil, for instance. So temperature then is another important aspect, and here we're looking at understanding Kelvin and Celsius, which are the same scale, but they're offset. So we think of Kelvin as the absolute temperature scale. So the bottom of the, I'm sorry, it's hard because there's a lot of stuff blocking my screen, so I can't see my own screen. I'll talk from memory here. So Kelvin starts at 0, and water freezes at 273 degrees Kelvin. And Celsius then is a offset of the Kelvin scale, so that 0 is the freezing point of water and goes up to 100 degrees. Most of us, I think, have a sense of Celsius because it's what the Europeans use, and Fahrenheit is our comfortable personal scale where we're accustomed to different scaling. So a lot of global warming science, for instance, talks about degrees Celsius. And when we talk about a 2-degree warming, it's usually 2 degrees Celsius that's being talked about. And so it's important to understand these different temperatures. So something they call the 0th law of thermodynamics is the principle of thermal equilibrium. If you have two bodies that touch, say body A and C here, they will equalize in temperature from their contact, as long as there's not an insulation between them. And if you have another body B that's in thermal equilibrium with C, then it turns out that A and B are in thermal equilibrium. So it's sometimes called the transitive property of temperature. So now we keep adding some more aspects of thermodynamics. We talk about pressure, and pressure is a force per area. So a force of a pound per square inch is a pressure that many of us are comfortable with. And so we put 30 pounds of pressure in our tires. That's gauge pressure. So it's gauge pounds per square inch, which means you have to add to that the 14.7 pounds of atmospheric pressure that are all around us all the time. So you actually have tons of pressure being applied to your body right now. It's actually amazing how much pressure is against our body, but of course we've evolved to withstand it. The Pascal is a very standard unit of pressure that down here you can see is roughly, well, it's defined as kilogram per meter per second squared. So the idea of pressure we think of with molecules moving. So on the right, there's a depiction of molecules that are moving around very quickly. So a gas, the molecules in a gas are moving around very, very quickly. And that's why if you have a shower in one room and you have a freezing window in another room, all that water vapor flies through. There's so much empty space in air that the water vapor will fly to that window and freeze. And so the idea of pressure is the bouncing of those molecules really against the surface. And that's actually how a thermometer works. Those molecules hit the glass of the mercury and pass kinetic energy into the mercury, and you can read the temperature. So pressure is going to come around, but right here, let's just talk about pressure volume equals the number of molecules times the temperature times what's called a gas constant R. So PV equals nRT, you might have heard of as the ideal gas law. And it's a very important thermodynamic relationship between pressure, volume, and temperature. And so this is fun because you can do this at home in your kitchen. You can actually derive the ideal gas law by making careful measurements of a balloon, putting it in the oven carefully to warm it up, and then releasing it, and you'll see that it flies to the ceiling. You can then put it in the freezer and you bring it back out and you'll see that it drops to the floor. So you can measure the dimensions, you can measure the size of this balloon, and you can kind of make an estimate of what those temperatures are as you change them. And what you'll find is that you can, in a sense, derive the gas constant R simply from this experiment. but it gives you also a very tangible and direct understanding of the relationship of temperature, pressure, and volume. So now we have force, we have pressure, we've talked about energy. Now we talk about work and power. So we look down, let's jump down to watt power. We're familiar with a 100-watt light bulb. Well, essentially that's the power that's being used in that light bulb. So power is a rate of doing work. So it's the expenditure of energy per unit time. I'm not going to go through all the details here, but one thing you might notice is that in this description, we see that we have a mass times a speed squared is energy. And if you realize the units, they actually connect directly with E equals mc squared, where energy is a mass times a speed squared. So this is basic, just basic relationships of energy, mass, and momentum. So now we look very quickly, just to make this a bit relevant to what's going on in the world today. Let's look at the total world primary energy use. And so here it's given in joules. We can say the total in 2019 energy that was used was about 600 exajoules. And 42 exajoules is a gigaton of oil equivalent. So GTOE, ton of oil equivalent is TOE. GTOE is a gigaton of oil equivalent, which is a billion tons of oil that's being burned. So you can see here you can actually calculate from the exajoules the amount of oil that's burned. And the US energy flow here again in exajoules in 1999, now it's not 2019, so it's 20 years earlier, US was roughly a quarter of global energy use, 102 exajoules. And here, this is a fascinating diagram that is very important for what we're talking about here, where we have the sources of the energy on the left, and we show how that energy passes into various subsystems of society, or particularly in the United States. So into electrical generation, into residential, commercial, industrial, non-fuel uses, transportation. And one of the things you can appreciate is how much of the energy is waste heat and how much is really useful. Through all of these processes of conversion to take these sources and turn them into useful energy for us in a home or in a car or in a machine, in an industry, we're creating waste heat. And you can see here, we only get about 40% of the energy actually applied. So now power is the ability to do work or to apply energy in a period of time. So back to our light bulb, let's say we have a 100-watt light bulb. That's going to be 100 joules per second. 1 watt is 1 joule of energy expended per second. Now, of course, you can have kilowatts, 1,000 watts, megawatts, which is 1,000,000, gigawatts, 1,000,000,000 watts, and terawatts, trillion. And what we see is that roughly megawatts is the power of a diesel locomotive, and power stations, nuclear power stations, can be a couple to 5 gigawatts of power generated. Now, the total global primary power, this is a fun diagram. For 150 years, we can see that it's steadily increasing. I show here, and this gives a projection also out to 2050. So the vertical red line down is year 2022. And so now we're looking at terawatts. So it's 1 trillion watts. Remembering that's going to be, a terawatt's going to be 1,000 gigawatts. And you can see roughly we're at 18 terawatts globally in the amount of power that we're using. I've got to keep clicking here to click here. So this is a fun quote from Lotka, who's a very famous scientist who looked at ecological dynamics. The Volterra-Lotka equation is used in population dynamics in ecology. But he made the observation that man has been unconsciously fulfilling a law of nature, according to which energy per unit time, power, in the system tends toward a maximum. And this is called the maximum power principle, and it's one of the core areas of research in evolutionary thermodynamics. But you can see immediately right there, is it true? If this is true, and you have a system like a government or like a bunch of corporations operating together, a law of nature may be driving them toward maximum power implementation. And the question becomes, can humans shut that down or even curtail it to a degree? So Carnot was a famous thermodynamicist in the 1800s. His father was actually one of the principals who helped Napoleon rise to power and helped decapitate the last king of France. But Carnot was a brilliant thermal engineer who brought around this concept of heat and work and the relationship of heat of work and the efficiency. So here now we'll bring in this term Q for heat, the energy of the system, and the energy passed from the environment or a source of temperature to a working body. And then you have some of that heat can be work, but you're going to lose some of that heat to your cold sink in order to do work. And that's the spent energy. So we have energy E, heat Q, internal system energy U, work done on a system W. And so a basic thermodynamic law says that energy is conserved, and the total energy of the system will be a combination of kinetic and potential energy, and the internal energy. The change in the system's internal energy will be equal to the heat entering the system and the work done on the system. So that's the first law of thermodynamics. We saw the zeroth law was the thermal equilibrium. Now we need to introduce the concept of entropy. And if you paid attention to some work by a guy named Jeremy Rifkin some decades ago, if you were alive decades ago, I think some of you were younger, he was claiming that entropy was going to do us all in, that every time we had any technology development, that we would end up with a more disorganized system. And basically, he didn't quite understand entropy. He didn't really grasp that everything that we do is basically a march against entropy. There's a very famous book by Schrodinger in the early 1900s called What is Life? And he talks about neg entropy, sort of the opposite of entropy, or moving toward lower entropy. And this is what living systems do, is create organization rather than chaos. So it's still a very important concept. Entropy is a measure of the thermal entropy, is the measure of the system's thermal energy per unit temperature. So if I keep the temperature the same and I keep putting more energy into the system, that energy has to be going somewhere other than temperature. And that can go into different aspects of the state. For instance, if I want to keep the temperature the same and I put a lot of energy into the system, well, maybe I use that energy to organize the system. So I'm trying to keep entropy roughly the same or lower the entropy. So you get this important measure of the various places and distributions of energy in the system relative to temperature T. And so you get the change of energy, and this is Clausius set this up, but this is actually called the Arrhenius equation by Swedish chemist Arrhenius in the late 1800s, where the change of entropy is the change in heat with respect to temperature of the system. So then we get to Boltzmann's reevaluation of entropy and the beginnings of statistical mechanics, where you create statistical entropy. And this is actually much more the way entropy is used now when people talk about information theory, and the amount of energy that you need for any particular piece of information. But this is related to the second law of thermodynamics. It basically says that in the universe, entropy will always be increasing, even if you're improving organization in a small local region. Finally, enthalpy is the total heat of a system. And one of the things I've argued is that enthalpy is really where we should be looking to try and understand what's going on with evolution. Some folks in evolutionary thermodynamics say that really all we're doing is maximizing the process of entropy. And I think that's focusing on the dissipation of heat from a system rather than looking at the increasing amount of energy that's being held in evolving natural systems. So enthalpy is H, and it's related to the internal energy plus the pressure volume changes on a system. Again, these are being defined in equilibrium systems. And then you have the Gibbs energy, which is very important in biology and chemistry, which is considered the energy available to do work in a system. And it's related again to the enthalpy and to the entropy. So you can also write the Gibbs free energy as a function of internal energy and entropy and pressure volume. And you can see here what we've done is replace H enthalpy with the U plus PV, pressure volume. So now you can get a summary of the first three laws of thermodynamics. And the third law is really just the statement that at Kelvin 0, at 0 degrees Kelvin, it's considered absolute zero. There's no motion, and entropy is therefore constant. Essentially nothing's going on. There's no vibration of any molecules. So there's essentially energy is quiet. So evolutionary thermodynamics is concerned with open systems, and it incorporates the study of non-equilibrium systems. And so there's a branch called non-equilibrium thermodynamics. Ilya Prigogine, probably one of the most important scientists in the 1900s in that area, bringing that science forward. Mathematics are very, very tough. And so it played out through a number of popularizers. Laszlo and some others Nicholas brought the work into broader discussion. But the basic idea is evolving natural systems go through a series of stages of self-organization from the micro world to the macro world. And so we can now say, what is growth? And an important concept here is that there's a radial aspect. Growth goes out radially. And it's fascinating when you think that radiation, when you emit light and energy just spreads, it spreads spherically, radially. It appears that when energy structures, it's doing the same thing. It's also going out radially wherever it can, wherever the structure is able to. So like an expanding balloon, and it's driven by a positive feedback between energy capture from the environment and developing methods to hold, move, and convert that captured energy into structure. So we can test this idea at the atomic scale, and you can realize that the entire periodic table is a radial accretion of energy, starting with hydrogen as the smallest energy sphere, but you just keep adding energy in this spherical dance, and you get larger and larger atoms. As you go to the molecular scale, typically we see a lot of early structures developing as, well, the ring structure of carbon is going to be fairly planar, but the molecules will tend to fill a spherical space. And the thing we see is you start to get aggregation of the atoms working together, and particularly important for life are the relationships of hydrogen, carbon, and oxygen, and add a little bit of nitrogen. Stanley Miller at UCSD was able to show that if you put these atoms into a flask and pump energy, that you'll be able to make amino acids. You can make very basic, complicated molecules. So at the very early biological scale, then you have the light elements learning how to use the heavier elements and essentially creating technologies like chlorophyll and hemoglobin. So an important portion of the captured energy is directed through some type of know-how or method, we could call it, to increasingly capture more energy from the environment for the energetic system. And so it's important to realize that know-how is essentially technique and technology. So we can look at this radial growth, and I like to point out that it's somewhat parallel to what's happening with the universe as a whole, where X, Y, and Z are the three dimensions of our three-dimensional reality. But you can posit a fourth vector, which I will call here the outward vector, an inward-outward vector, where the concept is that space may go inward infinitely. In other words, it doesn't stop at some point. You could just keep going smaller and smaller and smaller. And what we're finding is that when you go into this microscopically small space, you get enormous amounts of energy. And so it appears that coming the other way out of microspace, these energies are forming. At first, they're forming atoms at the tiny spot, and then they're forming larger aggregations where those assemble into chemistry, and those become larger aggregations. And you continually have this process where these tiny structures of energy become components of the next layer of organization. And they're doing it themselves from the inside out. They're continuing to grow up and form these next level of energetic systems. So this progressive process is called emergence and self-organization. And it appears that here we are as humans, we have components that are cells. Molecular biologists studying cells think of these as little, living creatures. Some of them even claim they have emotion. So it's fascinating as you move up, these components are alive and they have participated together to create the next level of organization. And that next level of organization is a living energetic structure. It's a living energetic system. And we've now done that again. We've now created a new layer of organization above the dimension of the human, above the scale of the human. So it's like the Matryoshka doll, basically, the Russian doll. So again, technology is method, technique, and here this amazing capability of the light elements to use magnesium first to create chlorophyll in plants, and then the same molecule figuring out, well, let's use iron when they start creating animals. So you have here really a wheelbarrow for energy. Both of these are moving energy from one part of the acquisition of energy from the environment to distribute it inside to the subsystem of the living organism. In one case, plant, the other case, animals. We've done the same thing again as humans. Just as the iron inside the hemoglobin circulates through blood vessels in us, now the human inside an iron car circulates through streets of the city. It's essentially the identical process. As above, so below. So in the 1980s, I worked on a restatement of evolutionary thermodynamics. Actually, evolutionary thermodynamics didn't really exist as a phrase back then. It's still not widely recognized. But focusing on how energy proceeds radially from and into energetic structure. Energetic structure disorganizes when the system falls apart, it dies, and the unbound energy diffuses radially, and energy aggregates radially in structure. So how do we start trying to approach this as a science and think about ways of describing more rigorously the energy that's in the system. And so what I realized was, let's create an observed boundary. This is an observer's boundary around the system. And of course, it's going to be somewhat arbitrary, and we'll have discussion about that, I'm sure. But it allows you then to use the radius as the way of assessing how much energy is actually inside your organized system. And so here you create an energy density where you start with the energy density and now let your radius change as a measure of the system taking on more energy. And so these are just definitions for thinking about this theory. What an energetic structure is, what an energetic system is, the organizational radius, the observed boundary. Dynamic coordination is a process whereby kinetic energies become harmonized, essentially. And it's a very important process of the growth of a living system. And then we'll talk about some subsystems. So again, setting the observed boundary is challenging. And here you look at it for a fuel cell. You can think about how you could do it for a city. Of course, wherever you try and put that boundary, you can think of energy coming in and going out that may be tied to a subsystem of that city. But it can be done in a crude sense, and it works for helping our thinking go forward. So I'm not going to go through all of this in detail, but basically you can look at the small d. This is just calculus. It's d means the change in energy. The dt is with respect to a tiny element of time. And so you're saying the change of energy with respect to time is equivalent to a force times a radial evolutionary velocity. This means the movement of this structuring process from the microspace into the macrospace. Essentially, you're looking at a force times velocity function. And so, we've seen that before in the previous slides. So now you can think of the force as a product of the pressure and the surface area inside this growing sphere of the energetic system at any particular scale that you're at, any particular radius. And so now you start to relate the force directly to the energy with respect to radius. What you can do is you move these equations around fairly simply. The 4 pi r squared just has to do with the volume of a sphere. And you now can relate the radius as a function of the force and the energy. And then you can basically take the radius out of the equation and collapse the relationship so that you're just looking at the evolutionary force, which is an outward pressure in essence on, if you're thinking about a balloon, you might think about this as the pressure pushing out on the inside of the balloon. We'll now think about it as energy structuring itself, being motivated to grow. So it's a growth pressure in a sense. And I believe it's a constant lambda, which is 4.836. That just comes out of the volume of a sphere relationships. But what you see is that it's a function of energy to the 2/3 power. And that's quite fascinating. This page here is just a summary, so you have all of the progression of those equations on one page. But what you get is this function. You get that the growth force is an increasing function of the energy inside the energetic system. And if this is the case, this is still theoretical. But what you're seeing here is that the more energy aggregates into energetic structure, the more the growth force. Now it's a tapering off exponential function. It's 2/3, but it still increases. Everywhere you are on that line, you're still increasing force. You're going to grow with the change in your growth as you acquire energy lessens a little bit. And it's interesting. You can almost think about this, the growth of a baby. They grow a lot in the beginning, and then we grow slower and slower and slower. But this sort of argues that you keep growing as you keep acquiring energy. Now, a human, unfortunately, isn't able to keep acquiring energy. We start to lose energy, and as your subsystems fail, eventually this structure falls apart. So energetic systems have subsystems, and there are many important subsystems. James Greer Miller in the 1970s wrote something called living systems theory. And I'll try and put something like that on the, find links to that to put on the website. But some of the most important have to do with storage, switching, transport, internal metabolism in living systems. And importantly, we're going to look at feedbacks. So the dynamic coordination among the subsystems is critical for the stability of the organism or the organization. And what you find is it's related to internal interference. So you're able, if you coordinate the subsystems, you're able to include in the system a lot more energy. You can have a lot more motion going on for the same amount of collisions against the walls of a city by cars, for instance, which might create temperature, like the molecules hitting the thermometer. If you coordinate all of those cars and have them run along roads so they don't bump into anything, they can go a lot faster. You can have a lot more momentum moving on the highway. So you can actually stuff energy into the system using dynamic coordination. And of course, that's how we got to be the organisms that we are. So now let's talk about an energy technology feedback. And this is really the important part of the talk, is that system functions that enhance incorporating energy that was previously external to the system. So if you're grabbing energy from the environment, any of those techniques will provide a positive energy feedback to the extent that the incoming energy can be used to enhance that acquisition function. So looking at this as a picture, the energy that's acquired, some of it goes into the next stage of acquiring energy. So you can think of this as if you're hunting for animals in the woods, you use some of the food that you eat, some of that energy goes into foraging around and finding more food. Now, for most species, that's a big chunk. A lot of that energy goes into energy acquisition. In a human society, that's our energy industry. The energy that we take out of the ground and fossil fuels, a lot of it goes to the energy industry to get the next stage of energy. So you can think of the energy resource, the subsystem is acquiring the energy, and then some of that energy is going back into the next acquisition process. Importantly, now we can think about know-how, which is information essentially, or knowledge, and we're putting energy into knowledge about how to acquire information and how to learn. And so you get a positive feedback in both of these are independent feedbacks in a sense. As we learn to learn better, now as we learn how to acquire energy, those things spin together. We have more energy to learn more, and we have more knowledge so that we can acquire more energy. So those are important feedbacks that multiply each other. Now, the energy technology feedback is a function of know-how, knowledge, method, technique, also the material technology that we're able to assemble. So as we've moved from, so we now have these huge machines that can suck oil out of the ground or crush the shale and extract it. We're getting better and more powerful machines together with our know-how. And then as population increases, we also have a pressure that increases the energy technology feedback. So it's got multiple parameters playing into the feedback as a function. It's also going to, so this means it's growing over time, and it's growing as a function of other exponential functions. So population has had exponential curvature for quite some centuries. That's slowing down, but we now have exponential growth in a number of areas of knowledge and technology. And that gives the energy technology feedback as its own process an exponential characteristic. So it's a growing feedback. Now, as we model the energy use in human society, here again are many of these factors that we saw in that earlier picture of extraction, storage, conversion, reserves. There's a lot to look at when we think about energy use globally. And we can we can begin to look at relationships in a network model of connections between all of these different subsystems. And there are many versions of them all around the world in each country, and they're all linked together. Global transportation system, global educational systems. So for an energetic system, you can now think about the energy that's being used in the energy technology feedback. Now, depending on your politics, you might think it's not such a good thing. But from the point of view of system evolution, the energy technology feedback is some of the most useful expenditure of energy for any growing system. So we can define a usefulness of this energy in terms of the percent increase in the energy technology feedback. And so we start to be able to get some handle on, well, how would we measure this and what might we do with it in a modeling exercise? So we can look at energy times a usefulness function, and economists have been using utiles, the UTIL, as a measurement of usefulness of money and various aspects of the economy. So it's not a completely new concept, but here we're using it in a way that we combine it with energy. And so we say utility becomes a new modeling component for trying to understand how energetic systems grow their energy use. So now we suggest that utility can be added to the whole modeling exercise. So what are some of the goals of tracking this metric? Well, you want to look at the spatial distribution, particularly the differences geographically. You want to look at the time development of this change. Is it accelerating? Does it go through dips? What's held it back? As we look at the momentum of these ETF-related energy flows through the subsystem, does it stay in balance with the other subsystems, or is there something peculiar about it? How independent is the ETF-related pathways? And what are the potential controls then? And might it be that that's where the controls need to be exerted? Of course, governments have tried to talk about carbon taxes, but it's not a very direct control on the ETF function. So now think about simple models of system growth. Here, let's talk about a single organism, and we just make it in a box. We have food coming in, so that's the capture rate of the energy from the environment. And then there'll be an internal use rate, B, and then we'll have some loss as the waste heat. So an organism works this way, and then there'll be, actually we excrete material too, as well as the heat, but certainly we perspire energy. We're cooling our body all the time. And then we can have a storage function, let's call it G. And now we can start adding components to our growing system. Let's talk about a system now that has parents and children. And so now, in a sense, the children become a subsystem of this larger system. And maybe we have a direct internal use of our energy by the parents. And we still get waste heat there, and we have waste heat from the subsystem. And we can then look at the storage and growth factors, and the waste heat is related to the work that's done. Now let's add a feedback. Now we start to add a feedback between the subsystems, between the children and the parents. So now some of the energy that's expended on the children are helping collect food, or they're helping do other things in the system. And so we can put that in. That's D here, where assist parents getting food is a internal feedback between the subsystems. So these are all ways that energy, if we're carefully mapping it between subsystems, can be put into a computational model. Now here you see this picture of in the center here, you see the distribution of the energy for the United States in the many different subsystems. And now we talk about the energy industry as one of our core industries that's working on extracting more energy from the environment. And then we have all the other sectors that are served by this energy industry. And now we talk about the know-how from many of these other sectors, the government sector, the educational sector, the machining sector, all that provide greater capability to the energy industry to extract more energy from the environment. So you can see the positive feedback there as these capabilities develop. So and finally, we'll talk a little bit about biospheric energy density of the biosphere as a whole is increasing in a couple of different ways. The residence time of solar energy coming through the system is being lengthened by various dynamic structural storage. The amount of solar energy being channeled through the biosphere is increasing. And that's because we're capturing more and more of it as much as we can. We grow more crops if we can. We put out solar panels if we can. Every method we use to extract energy is essentially extracting solar energy. And some of that we're putting into structure. Terrestrial materials are being pulled into our biosphere, particularly increasingly heavier elements. So we're pulling in the metals, we're pulling in the heavy materials to make our structures, to make our machines. So they become a greater part of this energetic system. So the biosphere is increasing in energy density. And what you can generally say is that an energetic system is attracted to energy. So it's a fascinating thing, but it may be that all energy is attracted to energy, that it's really a fundamental property of energy. So this idea that human societies are as alive as their components is very important if you actually take it seriously. And the thing to stress here is that we as organisms don't really think much about our individual blood cells or even how our blood cells are doing on a particular day. And if we want to run through the pucker brush to catch a rabbit, we'll scratch our legs and we'll let blood cells die on the sand, and we hardly notice it. And that's because there's not a direct communication that we understand at the level of life we live with our components. We feel them. Certainly they control us when they rebel or they fall apart or decay, but it's a very indirect communication. And if we begin to realize that the institutions we've created and that essentially the human society that we've created is a next level emergent living system, we'll begin to understand some of the constraints at our ability as components to control the directedness of that system and those overarching systems, because they have a life of their own and they live by optimizing their acquisition of energy for all of the feedback rewards internal to those systems. Now, we may think they're unconscious, but we don't understand what consciousness means at the level of those organizations. So key questions for climate change: how can we effectively find control points in our social system with regard to energy resources and use? Are our social systems doing something that's difficult for us to understand energetically? Is there a basic function common to all energetic subsystems of the Earth system that, if we do a better job of understanding through modeling, might help us locate specific governance points to engineer better controls? And there might there be some new parameters in our modeling, such as utility, that help us improve our view of the dynamic system. So research steps that are kind of upcoming in my mind have to do with assembling data, particularly putting it into a semantic graph database. And so these are semantic web approaches that allow us to reverse engineer dynamics of the system to develop a causal network model. And then using these data, you can begin to reverse engineer the dynamics and really look for the subtlety of what's going on. And then, of course, also develop simulations to test various attempts to control or at least limit growth. So learning to control growth, biological cells have a bit of a lead. They've been around for 1 billion years at least. And human social systems have been evolving, learning for less than 1/10 of a million years. So we're very, very new at this. Programmed cell death is an internally responsive limitation on growth that biology came up with. This is how biology does things. There's a method internally that says, okay, you've grown too much, that's the end of growth, you die. So can a living system limit its growth to arrive at a stable state without programmed system death? That's a very interesting question. Can components of an energetic system control the growth of the encompassing system? Again, I think an important question. 3 points then to take home from this exploration is that global warming is only a symptom. Stabilizing temperature may be important, but there's a fundamental growth principle that creates a much more serious underlying problem for humans as they think about the overarching organization or organism that we've created. And growth and stability functions are going to constrain our options and the options available to policymakers, decision makers. But we hope they can help us if we understand them, then maybe they help us make better decisions. This energy technology feedback is really a key to exploring the growth and stability. And I think it's important that we all understand it a bit better because it's really the driving force. It's not evil humans and it's not even evil corporations. It's something much more fundamental in evolutionary thermodynamics. So thank you. That was exactly an hour. I'm happy to stick around. Lily has said that we can take questions and I can turn the thing off. She may turn the recording off whenever she leaves or as she wants to.
We're good for a little bit. We're good.
So what do you all think? Let me turn off sharing my screen share. Remember, you can get to this on the website. Comments, questions?
Well, thank you for sharing all your information. My goodness, it's a lot to think about. So I'll be downloading your PDF to look at it more closely. That a lot of information there, and
yeah, I think it was a big dump, but
but I enjoyed the big picture and going from very small and on up to scales. That was very interesting to me, and trying to relate cellular development to like sociological levels of energy was very interesting. So yeah, I really enjoyed it, and it's a big topic. You know, it's
a significant topic. Yes, it is
for human beings to be on this planet and to be able to look at the big picture like this is like really incredible. So I really enjoyed a lot of it. I've been studying a lot lately about the emergence of life and all that. All that goes into that, and there's a lot of work being done now, and it's very interesting to hear your take on it. And I will be enjoying looking at your PDF shortly.
Well, great. And on the website, evolutionarythermodynamics.com, you'll see that I'm going to do a Zoom session in a month to invite any of you who would like to get into the readings and think more about this to keep the discussion group going.
So this is going to be outside of the Bethel University?
Yeah, it would be outside of Bethel University, and maybe next year we'd bring it back in for another round. But it would just keep the group discussion going for anyone who's interested. Maybe we do a meeting every month. It's like a book club or something like that.
Yeah, well, you got some good, a lot of information there to download. That's so I look forward to that.
Okay, thank you, Jim. Thanks for coming.
Well, thank you for your work.
Thanks. Dale's got his hand up.
Yes, that was very good, and about a year's worth of material. Well, by the time you have the conversations about each one, and so there's a good year's worth of material there.
I would say so, yeah.
So I'm, in fact, because of that, bear with me, I'm trying to figure out how to word this.
All right.
The human condition and our systems, but our systems interact with other systems. And in those systems, you get, I didn't hear you mention it, but it would be in the equations. You also get what's inertia. And
Mhm.
systems often will degrade when they start to run into inertia. But nature has a different take on that. I may be using the wrong words, so if you've got different words for this, that's fine.
No, I think I'm following what you say. Inertia, we think of as related to momentum. And
Yes.
so I think when you were saying you run into inertia, it's kind of like running into the brick wall. You're running into this slogging tendency where things don't want to move. In non-equilibrium thermodynamics, Prigogine did a great deal of work on this idea that it has to do with elastic limits. There's
Yeah.
a certain elasticity in the subsystem relationships and those dynamic relationships. And that after a while, as they get overbuilt, they lose their elasticity and eventually they break. And in a way, the movement of energy through the system has momentum. So there's almost an inertia to this massive amount of this oil and energy. Just the movement of these ships, they're moving, that energy's moving, and the flow of energy through the system has an inertia in a sense that makes it very hard to stop and resist.
Okay, so now that gets into where I'm trying to figure out the question to ask. I'm always seeing nature as at times responding to what we have chosen to do. So when I see a glacier melting in
Mhm.
Antarctica, I can't help but think there's a larger model out there that we don't totally have on paper. We don't totally understand how nature is responding to our choices, but we'll be in control as to how evolution will continue.
Mm.
May not even involve humans.
Well, so I think we kind of understand why glaciers are melting in various places. We certainly understand why there's greater melting at the high latitudes because of various aspects of geographical area and the movement of energy in the system. Your point, right. Your question, though, I think gets to this idea of, is there is there a God? Does God have a plan that's bigger that we're still playing around inside of and not quite understanding? That it's difficult. You try and apply science in a small local way to be able to get any traction. It's bringing spirit and God into this as something that could be measured or modeled becomes very difficult. But you have to remain open to the possibility, if that's what you're getting at. In other words, that there's an overarching plan of evolution that we're still stumbling to discover.
Yeah, because on a smaller scale, if I look at an ecosystem, anytime something degrades, something new develops.
Yes, yes.
So
yes.
If you take that and apply it to what I was trying to do on a bigger scale, I'm like, I believe that would be consistent. I just can't see what it is, but I believe it would still be true.
Yes. Well, life is enormously resilient as a process. If we believe that atoms are alive, and atoms have a lifetime, all atoms are created and then they die. And we talk about radioactive elements, those are just the short-lived ones. Standard stable carbon lasts for billions of years, but they're created. And so everything that we have here is in dynamic flux. It's coming and going. And we think that energy is conserved. So if one system decays, and another process will step right in and replace it. It will look different. We won't be able to talk to it perhaps, but it's still a living process.
Okay, and I got one last one. Well, no, it's definitely not my last one, but it's the last one I'm gonna speak about. You didn't throw any quantum physics into this, and I'd just be curious to know, have you gone there in your own thinking in terms of what happens? How do these systems change when I start bringing that into the picture?
Yeah. Well, it's fascinating, I think, to ask that question when you get down into these micro spaces below the size of subatomic particles. I guess we have to look at CERN lab for the best probing. And it's kind of strange. I think of the way they're doing it. It's kind of like they're coming up to these delicate little houses, trying to understand what's living in there and blowing them in with a bazooka, right? It's like smashing these particles together just to get some sense of what they're made of. But it may be the wrong way to inquire of what's going on at that scale. It does appear that some of the most recent physics around quantum theory, it seems to be pointing to this idea that we live in a hologram, in a holographic universe, and that that somewhere in the universe at some other scale, some other dimension, information may exist two-dimensionally, and it's somehow projected in three-dimensional forms to us, and that our brains are somehow a quantum. We have some interaction with the quantum field that turns it all into this 3D story that we have, but that essentially it's an illusion. And this comes out of things like the double slit experiment, but also particularly many experiments that show that things are happening ahead of time. In other words, the double slit experiment that throws quantum mechanics in our face is this idea that the electrons or photons going through a slit know the path that they potentially have, and they kind of end up selecting that path depending on what observer looked at them, or whether we're using a machine to look at them, or whether so how you look at something changes the reality of how it presents, how it manifests as matter. And that's very strange for our brains to grasp, this idea that maybe at the quantum level there is no structure, there are only fields that have all sorts of probability, or all the probabilities may exist all the time. And this comes to this idea that all time exists all the time. So all the future and all the past are all still in existence in the moment now together. And we make it into a past, present, future story because that's the way our brains have evolved to work. But that in reality, time really doesn't quite exist that way. And in reality, all probabilities only collapse into a reality based on the observer. So this idea that there might not be one single reality.
Would that be a closed energy system per se? I don't even think that's relevant. We're talking about
we
something
don't. Yeah,
else
we don't
entirely.
know. Yeah, we still don't know what the universe is. We're getting some sense of how light, how stretched out it is, and certainly our new telescope's going to help see a little bit farther back in time. But the universe is expanding from the inside, so it's not like from some center point it all goes out. The whole thing is every point in the room that you're in is expanding. So your body is expanding right now, and we can't perceive it because everything's expanding at the same, maybe not at the same rate. Maybe some parts of the universe are expanding faster than other parts. But the general idea that three-dimensional space is ballooning out at every single point of three-dimensional space, and maybe the growth of structure is informed by that outward pressure somehow.
But you also brought up the point And fractals tells you the same thing, like if you're trying to determine the actual distance of a coastline, where you're taking every little, you become as infinite going in
Right.
to the point of which is greater, or is that even a relevant question?
Right. You actually can't measure the length of a coastline.
Yes. Okay, I'm done. Thank you very much. I found this very fascinating.
Well, it's wonderful to have you and to have your questions. It's really fun. Thank you. Any other questions? If not, I invite you all in a month to come visit. I'll post you can contact me through the website, or I'm on Facebook, pretty easy to find. And I think, did we put,
Yeah,
this presentation has my contact information on the last slide. And thank you, Lily, very much for hosting this event.
yeah, you're very welcome.
Oh, very
All right.
good. Thank you.
Thank you. I look forward to checking out the website.
Oh, great. Thank you, Connie. And thanks, Doug. I
Thanks,
recognize some of the names.
Here.
Thank you, Joe.
All right. Have a very good night, everybody.
You too.
Andy,
Bye.
Bye.
Bye.